History shows a clear pattern. Economic and social expansion follows a revolution in the underlying infrastructure. Physical roads enabled commerce, the electrical grid powered industry, and a global fiber optic network created the digital age. That physical expansion has now breached the atmosphere. The world's foundational infrastructure is extending into low Earth orbit. This aligns with the infrastructure theory of civilization, which suggests that a society's economic reach is limited only by its infrastructural capability. For decades, orbital activity centered on scientific exploration and national prestige. Today, low Earth orbit functions as an active economic platform, an essential extension of the terrestrial digital economy. Integrating thousands of autonomous orbital nodes into a permanent digital foundation has replaced simple launch capability as the primary engineering obstacle. Modern economies operate on an invisible reliance on orbital assets. Satellites dictate financial synchronization, precision navigation, logistics routing, and disaster response. These orbital arrays require the same level of operational oversight as terrestrial 5G networks or edge data centers. As the boundary between Earth and orbit dissolves, terrestrial and non-terrestrial networks are merging into a single unified architecture. This deep dependency forces engineers to confront a new problem: how to ensure these assets remain operational and secure under every conceivable condition. A systemic failure in orbital timing synchronization now carries the same economic risk as a major failure in the terrestrial power grid. Traditionally, telecommunications, satellite systems, and computing evolved within isolated technology silos. These silos cannot support the demands of the modern data economy. We need a new blueprint, the Space Intelligence Convergence Model. Layer 1 consists of the space assets themselves, the satellite constellations and non-terrestrial networks operating in orbit. Below that lies the second layer, the terrestrial telecommunications networks, specifically 5G advanced and future 6G systems. In a converged model, these layers are linked directly. Orbital nodes connect with ground towers to form a seamless physical network. This physical integration eliminates the geographic limitations of traditional coverage, establishing a global data backbone. The third layer introduces the computational foundation, cloud platforms and edge computing nodes integrated directly into the terrestrial grid. Edge computing minimizes latency by processing data closer to the source, bypassing the delay of routing it back to a central hub. Managing the real-time complexity of this architecture requires thousands of microsecond decisions, a task far beyond the capacity of human operators. This necessitates a fourth layer, artificial intelligence acting as the native orchestrator. The AI layer handles spectrum optimization, anomaly detection, and predictive maintenance across the entire stack. Artificial intelligence transforms a static hardware network into a responsive, intelligent organism capable of self-management. This converged AI-orchestrated architecture is efficient, but it is also fragile. A localized failure can instantly cascade through the entire network. Extending standard terrestrial cybersecurity, like encryption or zero-trust perimeters, cannot guarantee operational continuity in this orbital layer. The principle of trust by design incorporates resilient engineering, responsible AI oversight, and transparent governance as foundational requirements, moving beyond traditional perimeter defense. This design philosophy relies on the 7 pillars of trusted space infrastructure to support the network. The first 4 are engineering pillars: trusted architecture, trusted operations, explainable trusted intelligence, and secure trusted communications. The final 3 are policy pillars: trusted governance for standards, trusted collaboration for cross-border partnerships, and trusted sustainability for long-term orbital stewardship. Trust is the foundational structural requirement that prevents systemic collapse. Organizations need a clear method to implement and measure these theoretical design pillars. The Space Trust Pyramid serves as a maturity model for corporations and national space programs. The base represents the baseline capability, protecting individual space assets from interference. Moving up requires integrating supply chain integrity, accountable governance, and interoperable standards. The apex is Tier 5, ecosystem resilience. At this level of maturity, the infrastructure anticipates, withstands, and recovers from disruptions automatically across the orbital, terrestrial, and intelligence domains. Achieving ecosystem resilience provides the stability required to scale the commercial space economy. The scale of this infrastructure means that no single nation or corporation has the resources to build it in isolation. Success relies on deep public-private partnerships and internationally recognized open standards to ensure hardware and data can operate across borders. India is currently positioned to lead this specific technological convergence. This advantage stems from a triad of capabilities: a mature space program, a massive domestic telecommunications ecosystem, and a proven, scalable digital public infrastructure. These domestic capabilities provide a blueprint for creating interoperable, trusted ecosystems on a global scale. Policymakers, system architects, and industry leaders must ensure that trust by design dictates the parameters of all future orbital deployments. The enduring success of the next digital civilization depends upon humanity's continued trust in the infrastructure that connects our world.